This is a new topic, topic 6, trigonometry. And this is lesson 1, exercise 4a, trigonometric ratios. The learning goals for this one is to understand how the trigonometric ratios relate the angles to the side length of a right angle triangle. The success criteria is to know the trigonometric ratios involving sine, cosine, and tangent, to be able to identify which trigonometric ratio to apply based on the information in a given right angle triangle, and to be able to use trigonometry to find an unknown side length in a right angle triangle. Trigonometric ratios is one of those topics that I believe is the most applicable in the real life world, both on the application side. A lot of carpenters use trigonometry, also to advanced fields of mathematics. It can be used in the music field, weirdly enough. I know we're talking about triangles and angles, but when you delve further into it, it can be used in the music field, it can be used in physics, lots of fields. So the study of trigonometry explores the relationships between the angles and side lengths of triangles, and more specifically, we'll be looking into right angle triangles. And so a right angle triangle is a triangle where one of the degrees is 90. And this is dictated by the little square here. Trigonometry can be applied to simple problems, such as finding the angle of elevation of a kite, to solving more complex problems in surveying and design. Now, Hipparchus, it's up for debate. Hipparchus was known for coming up with a table of values when it comes to trigonometry. So I believe he's one of the co-founders of trigonometry, and this dates back to 190 BC. So trigonometry, it's a pretty old topic, quite old in the fields of mathematics. And all we're looking at is the side lengths of a right angle triangle in conjunction with the angle inside it. And we're trying to look for relationships between these two. Okay. When I say relationships, I'll get to that later down the track, but before we do, we have to come up with some definitions before we can explore this. Okay, so let's just keep it as simple as possible. We're dealing with right angle triangles. Okay, we know that within a right angle triangle, one of the degrees is going to be 90. The other two is what we can try to either solve for or be given within a question. When a certain degree is given, we know what this degree is. When a certain degree is not given, or is the one that we're interested in, it's given this symbol here. And this symbol is a Greek symbol within the Greek alphabet called theta. Theta. And this is just, I like to think of it as an angle substitute. So this can be substituted eventually. Substitute. There we go. Substitute. So this will eventually be replaced once we find it out. Okay. So just like when there's an unknown length that we call x or y or z or a certain letter, theta is the unknown angle, or the angle of interest. With this in mind, there are three sides to a right angle triangle, and each three sides has a specific name. The one that remains the same, that is directly opposite the 90-degree angle, is called the hypotenuse. This is called the hypotenuse. The hypotenuse kind of sounds like hippopotamus, I always like to think. It's always the longest side of a right angle triangle. Okay, it's always the longest side. These two sides here will always be shorter than the hypotenuse. This one could be longer or shorter than the other one, we don't know, but we always know that the hypotenuse of a right angle triangle will always be the biggest line. The hypotenuse can be written as HYP for short, or the most shorthand notation is just the first letter, the letter H. Now, the angle here, which is theta, this depends, the names of the lines depends on where this theta or angle of interest is sitting. If the angle is here, then directly opposite this angle, which is right here, and originally is called the opposite. So this line here is called the opposite. O for shorthand notation, or OPP. Meaning that the last line here is called the adjacent, and adjacent simply just means next to. So this is the adjacent. And this can be written as either ADJ, you'll see some textbooks have ADJ, or simply the letter A for short. Okay, so this is all just simple terminology. Now I know that these lines could have been given simpler names, but this is the names that have been sprouted for this. So remember these set of names and rules were applied a long time ago, and we've just decided to stick to it. Now, when we have the angle of interest, or theta, up the top here, the opposite and the adjacent swap around. So everything still remains when it comes to the 90-degree angle and the hypotenuse, which is the HYP. The only thing that changes is where the opposite and the adjacent line is in relation to what our angle of interest is. So if we're looking at this one here, this line is now considered the opposite, meaning this line here is the adjacent. Now this rule is important because when we're given a question to answer, one line and one of the angles would be given, and we've just got to try to figure out a certain line from a question, where that line is in relation to what lines we've been given and what we're trying to solve for dictates what formula we have to use. So be very careful of this. Now before I jump straight into the formulas, and the formulas are quite confusing at first when you do look at them, we want to look into the relationships. Okay, we want to look at what Hipparchus was looking into, and all the mathematicians before him were trying to look into. What they discovered is that these two triangles here, they share a relationship of some sort. This 3, 4, 5 triangle here, and this 6, 8, 10, you can see that something is in common. And there's two commonalities. The first one is that this triangle here is exactly half of this triangle here. Because if you halve every single line, you'll get 3, 4, 5 respectively from 6, 8, and 10. So this here holds this half relationship. So there is a relationship of some sort. The second relationship is that the angles here and here are exactly the same. So theta, this theta is the same. This theta here, they are the same for this specific two triangles anyways. Theta is the same. And what the mathematicians back in Greece try to figure out is how and why. How do we know, and how can we try to figure out why? And so what they looked into is ratios between two lines. Okay, so they were discovering this. Okay, so let's put the mind frame of them trying to figure out what's going on. If I take this ratio here, or this line rather, and this line here, so this is the opposite and this is the adjacent, and let's just play around. Let's do the opposite divided by the adjacent. So 3 divided by 4. Okay, as a decimal, this is 0.75, so 3/4. Okay, and let's look at this triangle here, and we'll grab these two. This is 6, and let's just divide it by 8. When you simplify this down, we end up getting 3/4, which is 0.75 as well. Okay, and we know that theta in this case is the same, so they thought, there's a relationship between the opposite and the adjacent, and this angle here being the same. They couldn't really put it into words though. They couldn't figure out how do we actually write this down. Okay, but there is this link. This 0.75 or this 3/4 when simplified, there is a link. And they started playing around. They said, okay, why don't we not look at opposite and adjacent? Maybe we can look at if this is the angle of interest, maybe we can look at the opposite and the hypotenuse of both of them. So the opposite over the hypotenuse. So in this case, the opposite is, opposite the angle, which is 3. And the hypotenuse, which is opposite the 90 degree, is 3 over 5. Write that as a 5. 3 over 5, which is 0.6. So 0.6. They looked at this one. This is 6 over 10. When simplified is 3 over 5. So again, 0.6. Something's going on. We keep getting this same decimal, and we're expected to. Even though it's twice the size, it could even be triple the size or quadruple the size or half the size of this. It doesn't matter. There's this thing going on between the angles being the same and this decimal number being the same as well. And this is what trigonometry is about. It's looking and delving into this relationship. Now, unfortunately, the terminology behind it and how we write this out looks a bit intimidating at first, but just roll with it. Okay. So if we have this angle here, we know this is the opposite and this is the adjacent and this is a hypotenuse. The three terminologies that the mathematicians came up with is sine, cosine, and tangent. Sine, cosine, and tangent. Okay, so if this angle here, and we're looking at the opposite and the hypotenuse, we say that the sine of this angle, and we'll get into what the sine of an angle means in just a second. This is saying that the sine of this angle is equal to the length of the opposite side over the hypotenuse. The length of the opposite side over the hypotenuse. Okay, O, H, and S. I want you to keep this in mind. O, H, and S. So the sine of this angle, not sin, it's pronounced sine of this angle, is opposite of the hypotenuse. So remember, the mathematicians are trying to come up with some type of terminology. Now, this isn't saying that the angle theta is equal to the opposite over the hypotenuse. That's not what they're saying. They're not saying that the angle is equal to the opposite of the hypotenuse. They're saying the sine of this angle, which saw notation sin, is equal to opposite over hypotenuse. And I'm going to experiment with the calculator to show what this actually means. Okay. The second trigonometric identity is that the cosine is equal to the adjacent over the hypotenuse. So the cosine is equal to the length of the adjacent over the hypotenuse. So the only thing that changes within the right hand side is changing the opposite to the adjacent side. And if we use adjacent and hypotenuse, we use the cos or the cosine trigonometric identity. Again, we'll look into what cosine actually means if we delve into it. And the tangent is the opposite over the adjacent. Okay, so tan is opposite over the adjacent. So there are three different formulas that you can use when trying to solve for a side length. Okay, the shorthand notation of this is sine angle is over h, cos angle is a over h, and tan angle is over a. First letter of opposite, first letter of hypotenuse spells out S-O-H, which is so. First letter of cos, first letter of adjacent, first letter of hypotenuse spells out ka. And tan, first letter of tan, first letter of opposite, first letter of adjacent is toa. So ka toa is this thing that we use. I wouldn't really know what to call it. I like to think of it as some weird kind of chant. So ka toa, so ka toa. This will determine how to remember the trigonometric functions. That sine is opposite over hypotenuse, cos is adjacent over hypotenuse, and tan is opposite over adjacent. All right. If you come this far and you're thinking, okay, I sort of know what's going on, but where did you pull sine, cosine, and tangent from? I'm going to use the scientific calculator in order to further understand or better understand what's going on before we tackle these questions. Let's say I'm not going to even draw a triangle, give you some sides. I'm just going to draw a triangle. I'm going to put this as theta. Okay, and I'm going to choose the opposite side here. This is the opposite, and we know this is the opposite because it's directly opposite here. And we'll give it a certain amount. Let's call it meters. Now, I don't know what this is. This is just, I'll put a little rectangle. And let's choose a hypotenuse. Yeah. And this, the hypotenuse, is also some amount of meters. Now, we don't know what this is. Okay, so this is the hypotenuse, and this here is the opposite. Now, O and H, which identity uses O and H? Can't be A and H, can't be O and A, it has to be this sin. Not sin, mistake, sine rather. I was testing you. Its sine is equal to opposite over hypotenuse. Now, let's say this angle here, I'm going to make this 30 degrees. Okay, I'm going to make this 30 degrees. What I'm going to do is I'm going to grab my calculator out, and I'm just going to experiment. Okay, I can see the sine, cosine, and tan here. I'm going to put sine is equal to 30 degrees. Okay, and let's see what pops up. 1 over 2, half. I see. So this here, this length here, the opposite, which is the one on the top, has to be 1, and this length here has to be 2. And in fact, we can use the same property of sine being 30. Now I could have chosen any angle. Okay, this is 30 degrees. I can make this 2 and 4, can't I? Because the ratio, this can be doubled or tripled or halved. It doesn't matter. Okay, this was the link that Hipparchus was looking into. If I can find out what one of these angles are, I know what the relationship of these two lines must be. In fact, if I do sine of 45 degrees, there has to be a relationship of the square root of 2 over 2. I can do sine of any number between 0 to 90. I can do 80. 0.98. Doesn't have it specifically as a fraction. Let's do sine of 30. No, not 30. I just did it on 31. 0.51. So just a little bit over half. This here is what we're going to delve into. Okay, we're going to use the 3 different trigonometric identities here to help us solve for one of these sides if an angle and another side has been given. Okay, if you come this far, well done. I know there was a lot to take in, and I wish I could have used a whiteboard in the classroom to be able to show this a bit more clearer. But all I wanted to look into is using these relationships, or specifically this formulas here, to help us out with the questions. All right, there are 2 different type of examples that you are going to see. It's when the unknown is on the bottom and when the unknown is on the top. We'll look into these 2 examples here, and this is when solving for an unknown when it's in the numerator position, when it's on the top. Okay, let's see what we mean when I look into this example. So right now we're going to find the value of x in these right angle triangles correct to 2 decimal places. You will need your scientific calculator for this in order to tackle this type of question. Now the first one, we have a right angle triangle here. We've been given 3 pieces of information. The first one is what the degree is within the triangle and its position. The second one is we know that this line here, which is the longest line, the hypotenuse, is 11 centimeters. And this line here, which is adjacent to the angle that has been given, is some unknown centimeter length. We don't know what this length is, but we're going to use one of these trigonometric identities in order to solve it. Now there's a way that we solve for this. Okay, the very first thing I do before I solve this is that I always draw out the triangle. Now I know it's a bit silly for me to do this because I've already got the question here, but when you're copying the questions from the textbook into your book, it's good to have a visual guide to see what's going on. Okay, so we'll always recreate the triangle to the best of your ability. I'm doing this on tablet, so be patient. 27 degrees and 11 centimeters. Okay, so the first thing is I recreate this triangle. Okay, recreate this triangle. The second thing that I do is I label what sides I do know in relation to the angle that has been given. So theta is this angle here. I have been given the hypotenuse as it's the opposite of the 90-degree angle, and I've also been given the adjacent, which is next to it. So I've just gone ahead and grabbed the more simpler trigonometric ratios. So I've been given the adjacent and the hypotenuse. So the second step is to label what has been provided. The next step is I have to, knowing that I'm using the adjacent and the hypotenuse, I need to figure out now which trigonometric function uses the side lengths that have been given. And more importantly, in this case, which one uses A and which one uses H. Out of all three of them, this one here uses the A and the H. So we have to delve into cosine. The cosine of this angle 27 is adjacent over hypotenuse. Okay, so the next step is to figure out which trigonometric function we have to use. So we're using the cos of the angle is equal to adjacent over hypotenuse, A over H. And the next step is we're now going to fill in from the triangle what we can fill in here. One of these can't be filled in, and that's what we're solving for. So in other words, cos of 27 degrees, because that's the angle of interest, is equal to the adjacent, which is x in this case, over the hypotenuse, which is 11. So before we try to solve for this, what we're looking into is if I put cos of 27 degrees in my calculator, this is going to give me 0.89100, etc. In other words, we need to try to find the number that when it's divided by 11 will give me the same thing as cos 27. Once we find that number, we have solved for that length. Now, a lot of people will probably use trial and error or brute force, try different numbers, but this right here is a simple case of algebra. That is all there is to it. So we've chosen the correct trigonometric function. So the next step is to fill in what we know and solve. So fill in what we know and solve. So let's use or harness our algebra skills. We want to get rid of this 11, so we're going to multiply both sides by 11. And there's only one step to it. So this here, this x is, I'll put the x on the left hand side so we make this easier. X is equal to 11 times cos 27 degrees. This is how we solve for x. So when we put this into the calculator, 11 times cos 27 degrees, this is equal to 9.80 rather. 9.80, and I believe this is centimeters. Oops, try that again. There we go. So our x value is equal to 9.80 centimeters. So let's just recap on these four rules again. We have to copy out or recreate the triangle, label the side lengths that have been given within the triangle, choose a correct trigonometric function based on what has been given, fill in what we know, and then solve. And I know that seems a lot to take in, but the more you do this, the easier it gets, especially when the numerator is on the top. So let's do this with the second question, B, and we're going to copy this one out here. So the 90-degree angle is kind of slightly modified a little bit. It's on a bit of an angle. It's not laying flat on the sides. 90-degree angle is here. we know that this degree here is 69 degrees. This is 38 millimeters. And right here is our x millimeters, what we're solving for. Okay, first step, recreate or copy out the triangle. Check. Next step, label side lengths that have been given. Okay, so we know that this is theta. We know that we have not been given the hypotenuse. So the opposite and the adjacent are the only two left. We have to determine which one is which. So the one opposite the degree here is the opposite, and the one next to it is the adjacent. Okay, I always look for the opposite first and then the adjacent. Next is we're going to choose the correct trigonometric function based on what has been given. So we're looking for the one that uses O and A. Can't be this one, this uses O and H. Can't be this one, this uses A and H. So it has to be tan of the angle is equal to O over A. We're going to fill in what we know and then solve. In other words, the tan of 69 degrees is equal to x over 38. Now we know that in order to solve for this, all we had to do is multiply 38 out. But this step here, I wanted to show you how to solve it. It's just going to be the same process. There's just one step involved. So I know that x in this case is just simply equal to 38 multiplied by tan of 69 degrees. Okay, I don't have to write the times 38 times 38. We get it. We know. Okay, so let's just get 38 times it by tan at 69 degrees. Put this into a calculator. So 38 multiplied by tan, 69 degrees, close the bracket, and this is equal to 98.993. So 98.99, 98.99 millimeters. We know it's millimeters because it's been given in the context of millimeters, and that here is solving for the numerator on the top. Okay, so the steps are quite simple. You just got to use one of these three trigonometric functions depending on what you get. Next, we're going to look at what happens when what we're trying to solve for isn't necessarily on the top, but on the bottom as a denominator. All right, let's delve straight into it. Find the value of x in these right angle triangles. Round your answer to do 2 decimal places. A. Let's go ahead and recreate this triangle. Right angle triangle, right angle on here, angle being given here is 33 degrees, x meters, so we're dealing with meters, and 21 meters. All right, let's fill in. What do we know? We know that this theta here is the angle. This angle that is provided is the opposite, the O. And the one that's opposite the 90-degree angle is the hypotenuse. So we're using O and H. So which one uses O and H? It's the sine. So the sine of the angle is O over H. Or in other words, the sine of 33 degrees is equal to the opposite, which is 21, of the hypotenuse, which is x. Now, we're in a scenario where the x is on the bottom. When you have the denominator having the one that you need to solve for, the algebra behind it is we multiply both sides by h and then divide both sides by sine 33. The shorthand notation, a much easier notation, is we just swap these two. We just swap, okay? And this is strictly when x is the denominator. If it's the numerator, we don't do the swap. Okay, this is strictly when x is the denominator. Okay, so we do a straightforward swap. So our x is 21 divided by sine, not sim, goose, sine 33 degrees. So calculator out, put a fraction, 21 on the top, sine 33 on the bottom, 38.557, so this is 38.56. So x is equal to 38.56 meters. Okay, so little hack: when x is on the bottom, and only when x is on the bottom as a denominator, you swap the sine 33 with the x in order to solve for it. Last example before you go ahead and attempt the questions. I'm going to solve for this one. So the theory behind this, in my honest opinion, it is quite confusing to delve into it, but the actual examples itself, once you tackle them, they're quite simple. At first, you will feel a bit weird to know if you're doing this correctly. A lot of people walk into the problems of labeling their triangles incorrectly. Okay, the labeling is very important. If you don't label the sides correctly, you will fall into a lot of problems, especially when you check your answers and you're like, make sure you label them correctly. Okay, all right, drawing a triangle. That's our theta. What angles have been given? The hypotenuse has not been given, so I know there is the opposite, which is opposite the angle, and the adjacent. O and A uses tan, so tan theta is over A, or in other words, tan of 53 degrees is equal to 71.3 over x, which is what we don't know. Do swap when x is on the bottom. X is 71.3 over tan 53 degrees. So when using our calculator, x is equal to, clear that, tan, fraction first, 71.3, jumping ahead of myself, 71.3 over tan 53 degrees. 53.73 when rounded up, because that's an 8, 53.73. 53.73 centimeters. Chapter 4, along with its log sheet, which you can see right here, can be found in Compass Resources. There will be a new folder called Trigonometry. What questions you need to do is 1 to 4, 5, 6, 7, 8, 9, 10, and 11. Now, these are the minimum questions. If you feel like that you are running far behind, just remember that in this case, 9, 10, and 11 are deemed the extension questions. If you could just focus from questions 1 to 8, I'll be happy with that. If you want to extend it yourself, you can do question 9, 10, and 11. Trying to get this under 40 minutes. I think I did it 33 minutes or so. Best of luck with this exercise, guys. You know where I am if you need any help. We've got 2 days to work on this, Monday the 26th and Tuesday the 27th. Till then, I'll hopefully not see you in the next video. Hopefully we can get back to class. But if I see you in another video, see you then. Best of luck, guys.